Okay. All right. Let's try that. Let's see if it works. All right. So, so we're going to. So you have more potential energy. Well, we kind of deduced that. What was our intuition? When would this hurt more? If I had two balls and I'm going to drop them on your feet, which one would hurt more? Golf ball or the lead ball? Lead, right? So what's the big difference? The mass. Okay. So the potential energy here that we would be talking about, if we, again, using pain and suffering as a proxy, and we think about how much pain it would cause, more mass seems to be important. On the other hand, if I gave you the choice of me dropping the ball from 1 centimeter or 1 meter, well, we think that 1 meter would hurt a lot more too. So the height matters in that case. Okay. If you had a spring or a slingshot, and you pull it back a little bit, okay, it's not that bad. If you pull it back a lot, then it's going to hurt a lot. So it would have more potential energy. All right. So from a kind of conceptual point of view, here's what we're doing. In the case of gravity, let's focus on that one. Potential energy from gravity. Hope Emily could see that. All right. And I will abbreviate that with PE. Grav. Okay. So conceptually, what we are going to do is, instead of thinking about gravity as, you imagine this ball, one way to understand the energy analysis would be the ball starts with no kinetic energy, and then as it falls, it gains kinetic energy because it has more motion, so it gained kinetic energy. And the way you could understand that would be to say that the force of gravity performed work on the ball as it fell, and so the ball gained kinetic energy. So you could think of gravity as being outside, doing work on the ball, making it gain kinetic energy. So one way, so method one would be to say that we have a system, which was the ball, and on the inside, we have an increase in kinetic energy, and that's because the force of gravity did work on it. So we'd have a work from gravity. That's one way to think of it. Okay. The other way to think of this, kind of method two, which is going to be the preferred one, is to instead redefine the system to be the ball and the earth. And technically, although this semester it's not really relevant, what you're really doing is there's something called a gravitational field, which kind of fills the gap between the earth and the ball, and we're including that in the system as well. That's how we will talk about electricity and magnetism. We'll talk about charges, and then you'll talk about the electric and magnetic field as kind of communicating the forces between them. And it'll be very similar kind of conceptually. And so if you put the earth into the ball, which really means you're putting gravity all inside the system. There's no outside force. Okay, if I include the earth and gravity and the ball in the system, well, then there's no other force acting on it. So there's no work. So there are no input arrows or output arrows. There's no work being performed. That means that the total energy of the system can't change. There's no work. Okay. But the price we pay for including gravity in the system is that, you know, we still have a change in kinetic energy, but we also have a change in potential energy. So when you shuffle your definition of the system and you move things into the system, the consequence of that is that you oftentimes then have a potential energy associated with them. And so these diagrams are very similar. It's just I have a different system and I have to make sure to do all of the bookkeeping. So it's kind of like before, you know, when we started out, we were talking about markers. We were shuffling markers around. And I said, I don't care about the color. Okay. So if we only, with method one, so you could kind of imagine that maybe the black markers are kinetic energy and the blue markers are potential energy. So it just happens that with the first system, we only had black markers on the inside. But I didn't care about the color, but that just happened to be all that we have. When you redefine things, it's like saying, okay, now we have two flavors of markers. Well, don't taste the marker, but two colors of markers. That's okay. But as far as counting markers, we don't care. You just have to make sure to include them all. You can't forget some. That's the point. There are other kinds of potential energy beyond gravity. You can have a potential energy from gravity. Springs can be used to store energy. You can have stored energy in electric interactions, magnetic interactions, nuclear forces, right? Nuclear, you guys in chemistry, do you guys do any radioactivity or nuclear chemistry? None. Okay. In nuclear reactions, you use the fact, in fact, what we call mass and energy are actually the same thing, essentially. And so you can convert mass into energy using E equals mc squared. You guys heard of that formula? Einstein's mass energy relationship. So there are all kinds of energy, potential energies. We won't use most of them. The nuclear energies aren't significantly changing. And so we don't even bother to write them down. But they're there. And if we were to increase the energy level, you know, thresholds, so that you were just starting to cause nuclei to blow apart, then you would have to include that into the analysis. All right. Is this okay? Conceptually, what's happening? If you make the system very simple, so that it has no internal structure, or no, it's important, then all it can have is kinetic energy, and you have a whole bunch of work from the outside. Because you have to do the bookkeeping one way or another. If you make the system very simple, you have work from the outside. In practice, calculating the work is the hardest part of these problems. So if you can, your life is easier if you move things into the system, if you can. Okay. Now, it turns out not all forces can be pushed into the system. Only forces which are said to be conservative can be put into the system. And the main deal is basically, do they give the energy back? if you can get the energy back, so we like, if I raise this up, okay, the ball gains potential energy, and if I lower this down, it's back to where it started. Okay, that kind of force is a conservative force, and it has a potential energy. Something like friction it's stingy. It doesn't give the energy back. So if I slide this ball forward, friction took energy out. If I reverse the path, friction takes more out. It never gives that energy back. It goes away. It goes into heat and sound and other things. Okay, so forces which don't give the energy back, those are called non-conservative. So if you can, for conservative forces, put that interaction in the system. That will make your life better. Friction has to be on the outside. All right. Now let's come to some equations. The formula for the potential energy due to gravity. So let's imagine I have the floor here, and I have a ball, and it has a mass m, and let's say that the initial height above the floor is y. Okay. And yeah, the potential energy due to gravity equals the mass times g, 9.81, positive, times the height of the object, mgy. In high school, maybe they said mgh. Did you have that said in high school? All right. Since we're using, well, at home now it's sending me all the verification text. 30 minutes late. We already have the variable y, so I'm not going to introduce h all of a sudden. It's the same thing. Okay, so that's the formula for the potential energy. When you're on the floor, we'll say that it has zero potential energy. Really, we should be saying it's zero potential energy relative to the floor. You can choose any point as your reference point, and then you have to measure your height from there. But we always choose the floor to be zero, so that's why we do it. Okay. Very good. We still have kinetic energy, incidentally. What was the formula of the kinetic energy? Okay. So let's see how we could apply this. Let's assume that we have a ball at 2 meters above the ground. A ball at 2 meters above the ground, and for this problem, I'm going to give you the mass. Assume the mass equals, what do you think that is? Moment, what do you think the mass of that would be? 4 kilograms? Lower? What do you think? All right, we'll say 2 kilograms. Oh, I don't want to use 2 again. Sorry. Let's say 3 kilograms. Okay, 3 kilograms. If it's dropped from rest, from rest, find the initial kinetic energy. Sorry. Find the initial kinetic energy, find the initial potential energy, find the final potential energy, and find the final kinetic energy, and then use this information to find the final velocity, or the final. You really find the final speed, and then you have to use the fact that you know it's going down. Okay. And I want you to go through and draw an energy diagram to do that. So define the system. Identify, is there any work being done? Identify what's changing on the inside of the system. And then after you've done all that, write down the work energy theorem and evaluate all the quantities and use it to solve this. Pause the video. Okay, so this here. All right, so the work, so the way this works, the way any conservation law will work is once you identify kind of what the inputs and outputs are and the change on the inside, it always amounts to in minus out equals a change inside for whatever quantity we are talking about. For energy, now we have to include now potential energy. So in general, you could have work, positive work going in, you have some system, and you would have negative work going out, and that would, and you have now a change in kinetic energy and a change in potential energy. Okay. Okay, so sorry. So you have, it's always the same process. And what we would do is find the net amount in the arrows, you know, these count as positive, these count as negative, add them up with minus signs, you get the net amount of work, and that equals the total change on the inside. And again, just like with the markers, we didn't care about the color. We don't care about, when solving for energy conservation, we don't care what kind of energy it was. If it's changing, you just include it. So this would be the change in kinetic energy plus the change in potential energy. Okay, so this becomes the work energy theorem now. Including potential energy. So we have that. So then we can apply this to the problem at hand and just evaluate a lot of the numbers here. So to find the potential, or sorry, the kinetic energy at the beginning, well, in the problem I said it started from rest. So that would be 1/2 the mass times the velocity initial square. I put in the numbers and they get 0 because the initial velocity was 0. That was easy. I don't know the final kinetic energy right now, okay? I can find the initial potential energy. The formula for that was mg times y initial, and I can use my numbers here. So I would have 3 kilograms for the mass. G is always, what is G? Yeah, 9.8, positive or negative? Positive, always positive. Per second squared. And then the height, y initial, was 2 meters. So 6 times about 10 is a little less than 60. What do you get? 58.8 joules. Because a kilogram meters squared per second squared is a joule. Works out. Or remember, a joule is a Newton times a meter. Mg, that's the same. I mean, that's like weight. So that's a Newton times height. That's a meter. Newton meter is a joule. How about the potential energy at the end when it's on the floor? Final potential energy. Well, again, it would be mg times y final, but the final height is 0. So this is 0. Give me a thumbs up if you had all of these ideas. Yep. Very good. I have to erase this here, but I want to find the final kinetic energy and the final velocity. Passes. I'm sorry. So I need to find the final kinetic energy and the final velocity. And the way I'm going to do that is I'm going to use the work energy theorem that we just motivated. So we know that the total work equals the change in kinetic energy minus or plus the change in potential energy. Because we moved gravity and the earth into the system, there is no work from the outside. So the left-hand side now is 0. If you do this right, and my recommendation is that if you can, put all of the conservative forces in the system so that the only thing that's left out would be friction. I mean, that's basically drag and friction forces are the only ones that we've seen that can't be put in there, I think. All right. And, oh, I suppose if you have a rope, that should be put outside too. Okay. So you get 0 work and the change in kinetic energy. So that would be Ke final minus Ke initial. That's the change in kinetic energy. Plus the change in potential energy. Pe final minus Pe initial. I think you should write this equation each time and then plug in, rather than jumping to what you think the answer is, because you know this is guaranteed to be right. I mean, this is true if you do quantum mechanics. This is true if you do string theory. It doesn't matter. This is still true. So if you start at a place that you know is guaranteed to be correct and then do algebra, you're setting yourself up for success. All right. I know the initial kinetic energy, I know the final potential energy, and I know the initial potential energy. So I know all of these. I can use this equation to find the final kinetic energy. So I need to move. Well, some of these things are 0. You had 0 for the initial and kinetic energy and 0 for the final potential energy. So those go away. And I can move what's left to the other side. So right now, keep track of the minus signs. I have minus the potential energy at the start. If I move it to the other side, or get it by itself, I would have the kinetic energy final equals positive potential energy at the start. And looking at my math, I see that this has to be 58.8 joules. Okay. How many people were able to get that before me? Okay, so not so many. Do you see how I got it? And do you see where? So you start to use this equation when you start trying to solve for an unknown thing that you don't have other information about. So don't forget this equation. That's the kind of the whole point of the inner work of using energy ideas. Now, once I know this number, I can use it to find the final velocity, because I know I can now say that 1/2 the mass times the final velocity squared equals 58.8 joules. So I can multiply by 2, divide by a mass, and then take a square root. So I can get that the final velocity is, I'll leave a little space there. It's going to be multiply by 2, divide by the mass, which we said was 3 kilograms. And then I would have 58.8 joules. So it's about 40 square root of 40 is going to be 3 or 6 point what? So yeah, I say 6.3. 6.26. Oh, what units? Well, I know that's what we want, but how do we know that? Better check the units. So a joule is a kilogram times a meter squared per second squared. And a joule per kilogram would be a meter squared per second squared. So a square root of a joule per kilogram would be a meter per second. It's really worried. It's good. Okay, is that right? Oh, it's so close. Not quite. When we use kinetic energy, it's V squared. That means when you square this, it forgets about minus signs. It doesn't know. So you have to look at the picture and think about what's happening to get the minus signs. It's just like using kinematic equation 3 way back. In fact, it is kinematic equation 3. If you go back and you look at it, this is the same as kinematic equation 3, just rewritten. So you have to look at the story. When we took the square root, math won't tell us whether you should choose plus or minus. You have to think about the situation. And we know it's falling, so it's actually negative. Okay. All right. How do we feel? Yes. And then just solve it. That would work exactly. If you do that, you're saying don't plug in numbers, just write it out with symbols. Is that what you're saying? Yeah, like plugging in. Yeah, for kinetic and potential energy. You know what you would get? You would get, after you did, you would cancel. You'd have there's a mass in here, there's a mass in here. It would cancel because it's all equal to 0. Because I did that. Oh, okay. So we'll try that. It should work. What will happen is you do get kinematic equation 3. So let's see how that works. So we could say 0 equals, so that would be mgy final. I'm sorry, we're doing kinetic energy first. 1/2 mv initial squared, sorry, final squared. Sorry, struggling today. Minus 1/2 mv initial squared. So that's a possible place. Did you subtract the velocities and then square? Make sure you square it, then subtract. Okay, that's one place. And then over here, I would have plus mgy final minus mgy initial equals 0. Notice there's a common factor of mass. So I can cancel that. And then I could rewrite this to say, oh, and then I can multiply everything by 2 to get rid of this half. So I can multiply 2, 2, 2, 2. Multiply by 2, multiply by 2, multiply by 2, multiply by 2, and I can multiply 0 by 2, and it doesn't change. So right now I would have 0 equals v final squared minus v initial squared. Plus 2g y final minus y initial. Just regrouping these because it's common terms. And then I can solve for v final squared. And write that's v initial squared minus, because it's over. Or I'm going to write this as plus 2 times minus g times y final minus y initial. Kinematic equation 3, when the acceleration is minus g. So cadence, so it will work. I suspect what you did is you probably, some people subtract. No, you don't know the velocities. Oh, there you go. Yep. So that's it. Okay. It'll come out to be the same number. All right. Let's take a break and then we'll do more of this. All right. Pause. Okay. So let's start with another, let's do another example. So if there's a gravity problem, if you have a choice, unless the problem explicitly says that you should calculate the work due to gravity, it doesn't say that, I would always put gravity in the system and just use the formula for potential energy. And then you want the change in height from the ground. That's how I would always do it. So how do you think about this? And so think about that gravity problem we just did. We have an object, and as it moves, oh, and thanks for coming. As it moves, you can think of this as a conversion from potential energy at the start to kinetic energy at the end. And so you can just imagine the energy is just transferring back and forth between them. Another way coming up on Christmas, so you can kind of think about potential energy. So you can't look at something and just see its potential energy, maybe, but it's kind of like so in a physics problem, potential energy, it's kind of like Elf on the Shelf. It's the potential energy on the shelf. It's sort of like energy is like, you can like start maybe with kinetic energy, and then you can set it up on a shelf, set some aside. That's the potential energy. It's just there. And then later on, you can get that back. It's stored energy. It can be returned to you, as opposed and you can't do that for friction, because friction, once the energy is kind of handed off to friction, it won't come back. You just always lose more and more and more. And so for friction, you have to take care of it and think of it as a work being done, not as a stored energy. What about this? There's a ball in my hand, and then I made it move. How would you think about that from an energy point of view? Started with no kinetic energy in my hand and ball here, and then now it does have a kinetic energy. How would you think of that? Was that gravity causing that? Or no, so it's not a gravitational potential energy. Well, using the idea of a potential energy now allows us to have one way to think about the human body. Basically, how did this happen? Breakfast. Okay, I consume food. You guys can tell me all about the biochemical stuff, but there's energy stored in fats and sugars and blah, 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 blah. Okay, so that's all, it's a chemical potential energy. It's energy that it started as sunlight, gets stored in these molecules, and then it can be returned or turned into motion at a later time. So this is how you can think about biological systems, at least in part, okay, through the use of potential energy. Let's do another problem. Let's imagine we have, okay, let's ignore friction first. So let's say we have a hill. Let's say it is at an angle of 20 degrees. Let's assume we have a block and it let's say that the height of this is 1 meter tall. And let's assume that you know what? I won't give you the height. Let's assume that the initial velocity or initial speed is 3 meters per second. I would like to know, first off, how high above the ground will it reach? And then I would like for you to find the distance traveled along the ramp. So what should we call it? Let's call that the distance. Let's call that S. That's the distance along the ramp. Okay. And then we're going to ignore friction at first, and then we'll add that in afterwards. Okay, so take a second and define your system. Identify if any work is being done. And and you probably should draw a free body diagram here. So draw a free body diagram, identify your system, think about, is any work being done as it goes up the ramp? And then I want you to find the maximum height above the ground, and then just for fun, find the distance along the ramp. Just as a reminder, the formula for work is from a force is the magnitude of the force times the distance it acts, the change in position, which in this case would be S, right? The distance it would act, and times the cosine of the angle between them. So, and we also have kinetic energy, which is 1/2 mv squared, and potential energy, which is mg times the height above the ground. Okay, so take a second and identify the system, draw a free body diagram, and try to calculate final height and the length along the ramp that it travels. pause the video. Okay, so let's solve this problem. So we have a block going up a ramp. And we are ignoring friction right now, and it's just sliding upwards. You started out with a big push, but then you let go. It's just sliding up the ramp. It will come to a maximum height. So the free body diagram would look like, well, the weight would go towards the center of the earth, and then I would have a normal force, and normal forces are perpendicular to the surface or to the ramp by definition. So the motion would be along kind of up and to the right, the way I drew it, and the normal force would be perpendicular to that, which means that the normal force and the displacement will have an angle of 90 degrees perpendicular. Okay, so that's the free body diagram for the block. And then we want to choose our system from an energy point of view to make our life easy. I would say if I have a choice, then I always choose to put the earth and the weight into the system. So I won't have to worry about a work being done by weight. There could be possibly a work being done by a normal force. So for a moment, let's kind of contemplate that. I could have a work from the normal force, maybe. I make my system, make sure that's visible, may not be very visible. Make my system be the block and the earth, and gravity, all that in there. And if I do that, then I would have a change in kinetic energy and a change in potential energy to think about. So let's go into this a little bit more. The formula for work due to a force is the magnitude of the force. In this case, we'd have the normal force. The magnitude of the distance traveled, the displacement, that would be this thing we called S. And the cosine of the angle between them, which I said was 90 degrees for the normal force. The cosine of 90 is 0. So the work being done by the normal force is 0. And that kind of makes sense because if you think about how I described work last time, I said that work was due to the part of the force along the motion. The normal force is always perpendicular to the motion, so it doesn't do it. That's always the case. Very good. So in fact, when you go ahead and calculate the work due to the normal force, you just get 0, and this arrow is just gone. So it's a very simple system. It's simple problem from an energy point of view. All right. So if I don't have any outside work, I can simply say, well, so the work energy theorem says the work is the change in kinetic energy plus the change in potential energy. We just argued that this was 0. And so that will be kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. I know, the block goes up the ramp until it stops. We're trying to find that place. The final kinetic energy is 0 because when it stops moving, you get 0 there. And because the block started on the ground, I know the initial potential energy is 0. If I think about this, then I can turn it around and say that the final potential energy will equal whatever initial kinetic energy we had. So the block starts out moving with some kinetic energy. As it moves along the ramp, all of that gets converted to potential energy because because we ignored friction. So none of it was lost friction. Okay. Now I have to use my formulas. So I would say M times G times Y final equals 1/2 the mass times V initial squared. Again, I remember I said that the mass doesn't matter because it cancels from both sides. And I get that Y final equals 1/2 times G, by both sides by G, times V initial squared. And I can just plug in numbers. This is 1/2 times 9.81 meters per second squared. And the initial velocity was, what was it? You guys remember? Did we say 3 times 3 meters per second squared? What does that give us? Does someone have the number? We type that in. What do you get? You think? Okay. What number do we get? Somebody. 0.45. Is that I mean, how is that pretty close? What did you get actually?
I got 0.46.
46.
But I used the.
It's fine. You would have used it and then it would have canceled. You would have used it twice and then when you do the algebra, it should cancel.
I got 35
For
the initial.
Could be, yeah. Oh, could be. So that's the height. Okay, the other thing I asked for you to find was the length along the ramp. Or you had 0.46 when you include all the numbers, so we'll use 0.46 for that. So now, so here's the ramp. We know that this is 20 degrees, and we know that this is 0.46, Madison said. So blame her if it's wrong. And to find S, we just do trigonometry. So S was the distance along the slope. So I would say S is a hypotenuse. So I'd say 0.46 meters over S equals sine of 20. Turn that around. S equals 0.46 meters divided by sine of 20. And does anyone have a number on that? Sure. Okay, so that's how you solve that. Okay, let's reiterate the process. We identified the forces. That's just something we usually have to do now, always, with a free body diagram. And then we thought of made the system not from a force point of view, but from an energy point of view. We made the system be the Earth and the block so that we could put gravity into the system. So we didn't have to worry about the work due to gravity. And then the normal force was left out of the system. So maybe you could have had to think about the work due to the normal force. It just turned out to be 0 because of the angle. So then it was a really simple problem, and you just had to balance whatever you lose in kinetic energy, you gain in potential energy, and you just solve for the final height. It's just arithmetic. Okay. That general flow is how all of these problems will work. All right, let's take a 5-minute break and then we'll do another one. Pause this. All right, sorry, Emily, we got busy talking. Forgot to turn it on. So we're talking about springs and spring forces. So when you have a spring, let's imagine I had a wall and I hooked a spring onto it. And let's say there's a hook right there. So I imagine pulling in either direction. Okay. So in particular, you could imagine that if I let go, like right here, the spring just has a relaxed link. And when it's in a relaxed link, there's no force generated. It sits there. So you would first figure out where is the relaxed position. That's where it's in equilibrium. And then if you pull the spring to the right, there will be a counterforce going to the left. And if I compress the spring to the left, there'll be a counterforce to the right. The formula for the force due to a spring is called Hooke's law. It's minus K times X minus X relaxed. So if I make X bigger than X relaxed, that means if I pull it to the right, the force, this in parentheses is positive, and you get a minus sign telling you that the force acts to the left. And if I were to compress the spring, then X would be less than the relaxed position. This would be negative, and you'd have another minus sign, and the whole force would be positive, and you get a force to the right. This number out front is called the spring constant. And the spring constant measures how stiff the spring is. The units of the spring constant are newtons divided by meters. And the bigger K is, the bigger, stiffer the spring. A really floppy spring, I don't know, I didn't measure this beforehand. I'm guessing this one would be something like 2 or 3 or something. It's really small. Something like your garage door. Does anyone have, there are 2 kinds of garage doors. One where you have a coil above the door, and then another type where you have 2 springs on either side of the door. You guys never looked? Okay, if you have the ones on the side, I think those are usually like 100 to 200, but I might be wrong. But they're much stiffer because they have to support the weight of a door, not just a little bit. All right. Okay, so that's the force due to a spring. I want to think of it now more in terms of energy. So from an energy point of view, and again, so I can think about there being a potential energy associated with this spring, and kind of a proxy for potential energy is how much pain can be generated. So if I stretch the spring a little bit, there's just a little bit of pain. If I stretch it out more, there's more pain. So I expect that a spring that has been stretched out a lot will have a lot of stored potential energy inside it. It turns out the formula for potential energy in a spring equals 1/2 K, and it's the amount of stretch or compression. That's what this X minus X relative. Should have said that before. Or relax, sorry. It's that whole thing squared. This amount right here is sometimes called stretch. or compression. It's kind of, you figure out where it's relaxed, and then it's the kind of deviation away from that. Okay. Anyways, it's this thing squared. So what would this look like? If I were to graph the potential energy due to a spring, and I were to graph it, just write it up here. And let's assume that X, well, how would we do that? So where would this be zero? Where would the potential energy for a spring be zero? What position? Where what's zero? Well, it's not where X is zero, it's where X equals this. So if X equals the relaxed position, then this thing is zero. Okay, so this would be X relaxed. And then what kind of function is this? A parabola, yeah, right. And the size of K kind of determines how wide the mouth is, like how kind of strongly it veers upwards. The bigger K is, the tighter the parabola. If K is small, it becomes flatter and flatter. So this is a parabola. Yeah. It looks something like this. Okay. So this would be the equilibrium or relaxed position, where it's in the middle. And if you stretch it out, if you kind of pull, if you make X bigger than the relative position, the force will be to the left. If you make X left in the relative position, the force will be to the right. Okay. All right. I know not everyone has had calculus, but some people have. So I want to just point out something, then we'll go back to this example, because this is really important more generally. For gravity, the potential energy for gravity was mgy, potential energy. And the force was minus mg. That's interesting. So this one was linear, and this one was constant, and then there's a minus sign. Set that aside for a minute. Linear to constant. And then for springs, you have 1/2 K. Let's set the equilibrium position to 0. That'd be like X squared for the potential energy. And over here, I have the force is minus K times X. So I quadratic with a 1/2 becoming linear with a 1. In calculus, there's a process which does this. In calculus, what process do you have that takes a linear thing and gives you a constant? Derivative. Which, what visually, graphically, what does the derivative calculate? Slope. That's the general relationship. So here's the thing. The force up to a minus sign is the slope of the energy, but not a slope in time, a slope in space, position. So if you graph the potential energy as a function of position, the force is actually minus the slope. That's the actual thing. So that's something you should know, that the forces, and this is always true, forces are minus the slope of potential energy. So what does that mean? Let's think about this. Think about, okay, gravity. I gain potential energy when I go up. Okay. So that means as I increase height, the potential energy is growing. This minus sign tells you that the force will act to lower the potential energy. Well, okay, if I was standing up high, how would you have to move, or what kind of force would push you to lower potential energy? Down. So the force of gravity is going down because that's the direction to lower your potential energy. Okay. For a spring, what about if I'm over here? Which way is, tell me about the slope when I'm over here. Is it positive or negative? Right. The slope over here is positive, but the force is minus the slope. So if the slope is positive, the force will be negative. And that's why, so the force pulls you back to the middle. On the other side, here the slope is negative. So minus the slope will be positive, and the force pushes you back to the middle. Okay. This is why, and so you can see that when you have a potential energy, the forces will always kind of push you back to the lowest energy place. This is why in chemistry you talk about the ground state all the time, right? Right. In chemistry, you're always talking about minimizing the energy or finding the lowest energy state. The reason is that the forces associated with the potential energy are always pushing you to the lowest energy in that direction. And then the other thing you have in chemistry is effectively you have, it's kind of like friction. You can always leak out energy into the environment. So you're kind of, the forces are pushing you to lower your energy, and any excess energy you have is being sucked out into the rest of the solution or whatever. So it has the effect of just driving everything to the lowest energy state. So that's why in chemistry that the ground state keeps coming up. If you can have a really simple system where there's no energy loss, no heat loss, then it'll just keep bouncing around and it won't settle down into the ground state. It'll stay excited for a long time. Okay. All right. Okay. So in fact, although we won't do this, it allows you to imagine, something like this. Well, here's one. What if you had a system where the potential energy could look like this? Maybe it was up, down, up, down, up, down. You know what this could be? Okay. But physically, what physical scenario could you imagine? What forces push things to the ground state? This has many ground states, which basically means if you had a particle, like, I don't know, an electron, it might get stuck here, won't get stuck there, then it could get stuck here, won't get stuck there, it could get stuck there. It could be anywhere. It's a crystal. That's effectively what happens when you have a crystal. You have an array of atoms, okay? There'll be places where the electrons can be and can't be. When you go and you study this from an energy point of view and you write down the potential energy for the electron, you'll have peaks and dips and ups and downs and whatever. And these will be the places where it's stable. And then in a real system, these won't be the same height. So it might look more like this. It might be a peak and then a lower one, and then whatever. You could have all sorts of places. And what you would have are, you would have, this would be a place where it would be in equilibrium. This would be a place in equilibrium. Could be an equilibrium. This could be an equilibrium. This is not an equilibrium, maybe. All right. And then it goes down there. So what would happen is, classically, if it was just one electron in an atom, if it was here, it would be stuck here. And if it was here, it'd be stuck here, and that'd be it. However, there are always these kind of, in a solution, every once in a while it might get hit by some other atom or some other system. Something can bump it. And so this would not be an absolutely stable situation. This would be like a metastable state. So it might be here for a while, and then eventually, either through, maybe radiation, something would come along and bump it and drive it into a lower energy state. So these would be unstable, kind of metastable things. So if you were doing a chemical reaction, I don't know, maybe the lowest energy state might be to produce, I don't know. It might be that the model or molecule X, but it could be, so this might be represent, say, molecule X, but maybe there's sort of an intermediate thing that happens for a while. It could be like some other molecule Y. So you might kind of, a chemical reaction, sometimes you might produce this directly. Maybe you get stuck here, and then after a while, that fades away and it ends up as something else. Okay, so a lot of these energy ideas have direct relevance to chemistry. Why is it that when you talk about molecules, you talk about certain bond strengths? Okay, what that means is it's the same as the stiffness. For a spring, if you make the spring constant large, these become very steep. When you talk about the bond strength in a chemistry problem, what you're saying, something like the effective potential is very tight. And so basically, if the electron is here, it's very hard for it to get out. That's a very tight bond. If it's a loose bond, that's like a floppy spring, and it would just look very shallow, and then it would be very easy. It wouldn't take very much force to push it away from the minimum. Okay, and so bond strength, this is a very good way to kind of mentally think about what's happening. You can think about an electron approximately in an atom as being connected to the center of the atom by some sort of spring. The stiffer the spring, the tighter the bond. And then that also controls the relative size of the atom and the molecule and things like that. Okay. All right. Those are things, we will talk a lot about this in physics too, as we talk, because we will talk about electrons and protons and forces between them. We will talk about that. Now, I will tell you also, when you go to apply these ideas to atoms, you can't ignore quantum mechanics. So some parts of this story are kind of the same, and other parts are modified. So you have to worry about that. Okay. But in organic too, I think you guys will do spectroscopy, and you will look at, you'll look at shine light on a molecule. You will see resonances. You'll see peaks and dips and things, and read off what chemicals are in the solution. And what you're really doing is, what's actually happening is the electrons are jumping kind of from place to place, and you're looking at the relative energies. You're looking at what happens is a difference in potential energy it determines the energies of the photons of light that can come out. And so you can go, once you know that, you can deduce the strengths of bonds and things from that. All right. Let's stop there. Stop there.